Welcome, reviewers of our article on advancing training data techniques for 60-pose localization via object detection. Our research challenges some of the conventional wisdom in training neural networks for computer vision by demonstrating that using certain training and labeling techniques can significantly improve the pixel-level accuracy and robustness of object detection when used for 6D localization. Specifically, we show that augmenting the training data with object components that are normally occluded, correcting for perspective distortion, and avoiding scale augmentation during training can all lead to better performance in 6D pose localization. We will discuss the theoretical underpinnings of these techniques, provide empirical evidence for their effectiveness through extensive simulations, and offer insights into potential applications in real-world settings. The main purpose of our research is to find the sixth degree of freedom, position, and orientation of a receiver aircraft when viewed from a tanker aircraft's rear camera. This is intended to enable the task of autonomous aerial refueling. In short, where is the plane in the image? The overall prediction pipeline functions by capturing an image, running the neural network against the image to find bounding boxes on components of the aircraft, then using the centers of those bounding boxes to make 6D position and orientation calculations for the aircraft in the scene. However, if we train our neural network on components of an aircraft that are defined in the typical way object detectors are trained, then issues arise. The typical way is to define a component, seen in this image as a point cloud, project those points to the screen, omit points that are occluded, then draw a box around those points. The issue from this is that the 3D geometric center will not match the center of that bounding box, which means the perspective endpoint calculation could be incorrect. This is for two reasons. The first is that if a portion is occluded, that will directly shift the 2D center to whatever is visible. The next is due to perspective geometry, also called perspective distortion in the photography community. This image shows our technique for correcting that distortion. We expand a bounding box to match that new bounding box's center to the 3D geometric center's projection. The math of perspective distortion respective of the mismatch in 2D and 3D center points is better diagrammed in the journal article itself. But this dynamic slide shows a simplified example about how the projection of an object to an image sensor could cause a mismatch in the 2D bounding box center and the 3D projection center. Perspective distortion can be a difficult concept to grasp, due to the human brain's ability to easily interpret images and the unique characteristics of the human eye having a curved image sensor, which differs from the flat sensor in typical cameras. Also, many people are familiar with perspective distortion from real estate imagery and think it's simply lens tricks that are used to alter the appearance of objects. This means it can be challenging to understand precisely how perspective behaves and impacts the visual representation of objects in an image. The lens as a cause is a misnomer. The true cause is the location and orientation of the observed object compared to both the position and orientation of the camera's flat image sensor. This concept then leads to the fact that an object's position and orientation versus a camera will cause the object to have a distinct appearance in an image. This is important to the neural network community because augmenting imagery during training by the typical methods will affect that distinctive appearance and the amount of mismatch and center point correction that is trying to be learned by a neural network. The key concept to communicate here is that the center point correction being learned is proportionally different based on all of these criteria. This brings us to the goals of this research: to show the necessity of these labeling techniques to our use case, the ability of the network to learn to correct for perspective distortion and predict occluded features, to identify the augmentation techniques affected by perspective distortion during training, and investigate what is actually being learned during training. To do this, we designed some experiments. First is an ablation study training multiple neural networks where we quantitatively show the necessity of correcting for perspective distortion and labeling occluded points. Next, we train multiple neural networks with different combinations of imagery augmentation parameters used during training in order to identify the optimal combination for our use case. Finally, we test if the position in the image negatively influences the perspective distortion correction applied. To conduct that test, we took 520 images from the test set and overlaid them onto different portions of a larger image of the sky. The pixel dimensions of the overlaid image were consistent with those used for training due to the fixed nature of receptive fields in CNNs. This resulted in 10 new datasets for comparison, 9 from positions in the image observed on this slide, and 1 from conducting inference on the original images. This allowed us to investigate whether the distinct appearance of an item was being used to correct for perspective distortion, or if the location in the image had an effect. This is important because in a real-world system that focuses on speed, the image that is provided to the neural network may be a segment of a larger image to speed up that processing. While various detailed metrics are available in the tables and figures of the journal article itself, the primary outcomes of our experiments revealed that incorporating occluded components during training was essential. It raised the proportion of observations from our 5,000 point dataset, which met our 7 centimeter threshold, from 65 to 80%, representing a 15% increase. For the perspective distortion correction, as anticipated, the experiments also demonstrated that executing our algorithm without correcting for perspective distortion was not feasible. However, it was intriguing that without center point correction, it was occasionally able to make predictions within the error threshold. For the experiment focused on the best data augmentation, we tested networks trained with and without mosaic, translation, and scale, because that was what our analysis of perspective distortion indicated were potentially related to the appearance of an object and affects the amount of center point correction required. The original set of parameters had each of these enabled. When training without mosaic and translation, this reduced the number of components that were found and slightly increased the 2D error, resulting in worse 3D performance. Conversely, training without scale increased the number of components found and decreased the 2D error of bounding boxes, resulting in an improved 3D position and orientation. These amounts were very small, but did show significance when utilizing Wilcoxon rank sum tests with an alpha of 0.01. Finally, on the test bearing the position in the image and if that had a negative impact on the 2D error, it was found that there was no significant degradation in the predictions between the positions. In fact, as the image was moved further away from the edge of the image, the false positives decreased, and even improved the 2D error of the remaining bounding boxes. The assumption here is that when content replaces that which was normally a complete feature, that is not the feature, negative feedback is created, allowing the network to decide that the component feature is not there, and to not utilize that for assisting with the other component's locations. This led to a short examination of the false positives. Manual verification showed they were all features whose center points were slightly off the edge of the image, causing them to not be labeled. These plots show the numbers of false positives, with the left plot showing based on the location in the larger image from the latent space test, and the right plot showing false positives based on where the center of the aircraft is within the image. The false positives when the aircraft was near the center of the image were from the aircraft being very close to the camera, allowing its 3D center to be near the center of the image, and for its components to also be off the edge of the image. This leads to a potential extension of our work, to train the network to identify components off the edge, potentially decreasing the overall error. The research findings demonstrate that knowledge of occluded components can improve the ability of neural networks to detect components on larger rigid objects. Also, when using neural networks for pixel-level precision that is required for navigation, it is important to consider how perspective distortion affects the appearance of objects and images, revealing that during the training of CNNs, there is a trade-off of using imagery augmentation due to perspective geometry. While the tendency in object detection is to focus that augmentation to increase the number of true positives you can find, that may come at the cost of pixel precision. In this specific application, the overall impact of scale was found to be negative, while mosaic and translation had positive overall effects. Finally, we saw the position of the object in the image did not negatively affect pixel precision, indicating the network was able to learn the distinctive appearance of the object and use that to correct for distortion. This work also revealed that our training technique pushes the CNN to make predictions with less visibility of components, resulting in false positives near the edge of the image. Hence, in future work, we plan to extend these concepts to off-image components. Thank you for your time. Please send any questions to my email on the journal article.